Dr.N.Mani sir, Professor, Department of Mechanical Engineering, Sairam Engineering College. He is specialized in design and fracture mechanics. He has more than 19 years of teaching experience. He published many journals in international, national, and conferences. At present, he guiding research scholars under the Anna University. He has more than a professional body members. Now I hand over the session to Dr.N.Mani sir. Thank you, sir. Thank you for your presence, sir. Thank you, sir.
Thank you. Thank you, sir.
Thank you, Mani.
Yeah. Can we start now?
Yeah, yes, sir. Yes, sir.
Yeah. So I'll stop my video because I don't know how the data will be. Yeah. Yeah. Good morning, everyone. Have a good day today. And today I'm going to handle the topic of phase change materials. And nowadays, almost everywhere they are using this phase change materials because of energy demand. Because we are always depending on some fossil fuels. So nowadays, the entire scenario is changing, and we are moving towards green energy. And those green energy may be by using phase change materials or the phase change for the few materials. By doing this phase change, how the energy is stored and how the energy released. So those things we are going to discuss in the starting part. And with the example and with the small product, I'm going to complete the session today. Yeah. So global demand for energy is growing rapidly, and higher consumption of fossil fuels leads to greater greenhouse emissions, particularly carbon dioxide, NOx. So those things are releasing too much by the fossil fuels. But whereas at present we don't have any option to depend on remaining, because we are almost dependent on only fossil fuels, and which contribute to creating heavy environmental impacts. So that is a problem really we are facing. And in the summer days, we are almost facing global warming, right? So too much of hot. So that due to this, we are always depending on fossil fuels, and our vehicles, automobiles, emitting too much of NOx, right? So due to this, we are facing day by day problems. And apart from global warming, we are facing ozone layer depletion and climate change. And only for a few months, due to this COVID-19 effect, the climate is a little bit normal, right? As you know, the entire world is facing very greenery, right? The main cause for the intensified energy consumption is the overall change in the living standards. That is the main problem, right? So normally summer days, or when we are in the hot place, we need some cool. And when we are in the cold regions, we need some heat. So that is the reason why we required more amount of energy, why the demand is growing higher. Because of living standards, because we cannot live as it is, because our body is tuned to a new environment, right? So that is the problem for heating in the cold regions and cooling in the hot ones. So this is the problem why the demand is increasing day by day. And this is the energy consumption released by IHS by 2019. The total energy almost consumed only from fossil fuels, almost more than 80%, natural gas, coal, and oil. So most of the energy is consumed only from these fossil fuels, especially these three. And whereas if you look at renewable energy sources, it's very less percentage. And if you take how the energy is distributed through different sectors, right? So total energy is consumed only from these fossil fuels. Those energy how we are distributing to different areas, right? So maximum energy is distributed to industrial sites and transport and domestic purpose. And if you try to incorporate our renewable energy sources in industry and transport, almost the maximum amount of the greenhouse emission gases will be reduced, right? And this is a small example I'm checking. And this is by 2018. If you look at the coal is 38%. We are depending on coal 38% for energy, and natural gas 23%. And if you look at renewable energy sources, that will be very, very less, 16 plus 2 plus 5 plus 3. That's it. 21, 24, 26%. And based on Paris Agreement, right? Paris Agreement. The main objective of Paris Agreement is we have to hold the increase in temperature, increase in average temperature below 2 degrees Celsius before 2040. So we have to, because year by year, day by day, the temperature is increasing. So we have to hold the increase in temperature below 2 degrees Celsius for another 20 years. For that, what are the things we have to do? We cannot depend on, again, fossil fuels. If we depend on fossil fuels again, the temperature will be increases automatically. So that is the problem. We are moving towards the renewable energy sources. So an actual plan for, based on Paris Agreement, is the renewable energy sources by 2040, more than 60%, so more than 44% will be depend on these renewable energy sources. That is the Paris Agreement given, that is the standard policies, and that is sustainable development, right? 2040. So how we are going to face these new changes, right? At present, we are facing the almost the new one, right? COVID-19 throughout the world. Same way, we have to change ourselves towards renewable energy sources. If we depend on again fossil fuels, the Paris Agreement will also get failed, right? Because the plan for the Paris Agreement is we have to reduce, or we have to sustain, we have to reduce the increase of temperature, right? That we have to take care. For that, we have to depend only maximum depending on the renewable energy sources. And this is the total energy consumption. As already in the previous slide I said, the maximum will be from buildings, that is infrastructure and industry. And if you take that buildings, we are consuming 10% from electricity, 20% from coal, and 30% from renewable energy sources, and natural gas from 10%. And still further classification, how much amount of CO2 emission from 31%. So direct CO2 emission is 30%, and 70% will be indirect. That is from natural gas, renewables, coal, and electricity. So this is the problem why we are moving towards renewable energy sources, right? For renewable energy sources means we have to reduce the greenhouse emission gases. So for that, what are things we can do? So that is the things we are going to discuss today. For that, one thing is we can store latent heat, right? So thermal energy storage is a useful tool for improving energy efficiency and increasing energy savings. So how to increase the energy savings and how to improve the energy efficiency, right? That is the main tool. That is the thing we are going to discuss today. What is thermal energy storage? And here we have 3 different kinds of thermal energy storage. First thing is chemical heat. This chemical heat will be by breaking and forming molecular bonds. And the second one is sensible heat. This is by heating or cooling a material. So without any phase changing, just like that, we have to heat and we have to cool directly. There is sensible heat. And third one is latent heat thermal energy storage. That is by, we know, different phases, right? Melting, solidifying, those kind of phases. So by melting and solidifying a material. So how we are going to achieve this thermal energy storage? By using these 3. Now out of these 3, we are going to concentrate only on latent heat thermal energy storage. And why we need this? This thermal energy storage, why we need this, right? So as I said, energy demand vary daily, weekly, and seasonal basis. Seasonal basis means in the some more amount of heat. So that is a seasonal basis. So those points we are almost receiving more amount of energy, more amount of electricity we are spending. So that's why the energy demand increases during this seasonal basis. And this thermal energy storage is helpful for balancing between the supply and demand energy. So how much supply and what is the demand? So we have to balance this. So if balance is not there, again we'll get day by day problems, right? So power cut problems will face almost daily life, regular life. So that's why we have to balance this. What is the amount of energy supplied and what is the amount of energy demand? So we have to balance these two. And this is defined as the temporary holding of thermal energy in the form of hot or cold substances for latent utilization. So same way what we are doing in the inverters, right? We are storing the energy, and whenever required, the inverter or battery releases the energy. That is thermal energy storage. We have to store energy in some point, somewhere, by using some components, some materials. So that is called thermal energy storage. How we can store the energy, right? So temporarily, not permanent, right? Temporarily, we can store a certain amount of energy. Then whenever required, right, we can release energy. And this deals with the storage of energy by cooling, heating, melting, solidifying, and vaporizing. These are different phases of the material. We can cool the material, we can heat the material, we can melt the material, we can solidify and vaporize, right? And thermal energy becomes available when the process is reversed. When we cool the material, it gets solid. When we heat the material, that will get liquid state, right? And this is the inversion process. So by this phase changes from solid to liquid or liquid to solid, the energy will be stored and the energy will be released. So when the energy will be stored, when the energy will be released, right? That is the thing we are going to discuss. So this thermal energy storage systems for a particular application depends on. So these are the categories, because just like that we cannot do, right? So this storage system will be depend on storage duration. So how much time, how long time we can store the energy, and cost, economics, and supply and utilization of temperature requirements. So what are things we can utilize? Like for example, if you take that inverter, right? So we can use only not heavy objects we cannot use, like mixie, AC, that we cannot use for normal inverters. So that is the utilization of temperature requirements. So how much we are utilizing from the stored energy, from the energy storage device, right? After storing, then storage capacity. So how much energy we can store, and what is the heat loss and available space. So all these things we have to take into consideration while we are, right? So how much time it will get, what is the time of duration, and what is the amount of energy stored, and what are things we are going to utilize for the available energy. So these are the main criteria, main things we have to take, we have to consider. Then peak shaving. Peak shaving is nothing but proactively managing overall demand to eliminate the short-term demands. That means we have to manage, we have to level out the peaks. That means when the demand is more, that time will get problems. So if you take any graph, if you plot the demand, so some places we will get peak. So we have to level that peaks by eliminating the small demands. If you reduce the small demands, automatically the curve will be leveled. That is the peak shaving. So how to level out the peaks, right? So this is the storage energy for different materials. If you take small example of 10 millimeter thickness of different building materials. So in the graph I given a different building materials. So like glass, wool, wood, plaster, concrete, iron, water, and some PCM, phase change materials. If you take 10 millimeter thickness of this material, and if you heat from 18 degrees Celsius to 26 degrees Celsius for 24 hours, how much energy is stored by different materials? That is the graph shows. So this is the unit in watt hour per meter square. If you take glass or wool, it takes only 2 watts hour per meter square. If you take wood, 18, plaster, 23, concrete, 48, iron, 79, water, little higher, 93, right? So already we know how much energy is stored by the water, right? And at last, phase change materials, 288 watts per meter square. So that's why we are depending on phase change materials. So already I said renewable energy sources. So from that we moving towards phase change materials. So by using this phase change materials, how we can save the energy, how we can little away from regular fossil fuels, how we can reduce the greenhouse emission effects. So that's why we are moving. Based on this graph, this data, the more amount of energy stored by the PCM, right? More amount of, that is, if you compare with the remaining regular uses material, right? These are the materials regular day, regular life we are facing and we are using. So if you compare with the regular material, the PCM materials will store more amount of energy. So that's why we are moving towards PCM. So what is phase change materials? So these are the substances that absorb and release large amounts of thermal energy. So that's what I said. So during one phase of change that will absorb the energy. So another phase of energy that releases the energy. So when it absorbs, when it releases, right? So the absorbs and release a large amount of thermal energy while melting and freezing. From when the phase changes from solid to liquid, that is melting process, right? The energy will be absorbed. When the phase changes from liquid to solid, that is freezing, the amount will be released. If you, because almost all the houses we have a refrigerator, right? In the refrigerator we have a small box or ice cubes, ice packs they are giving along with the refrigerator. So those are called PCMs. If you look, that is almost in the melting stage. That means that stores an amount of energy. When the power is cut, when the power is not there, that PCM material, that box will give energy to the refrigerator for next few hours. So that's why we are having that PCM materials, right? Thus, that phase change materials, when it melts, that is actually in the liquid state, that means it melts. So that means that stores some amount of energy. When the power is not there, that releases the energy to the refrigerator to make it cool for next few hours. That means the object, that is the liquid or gel, what is there in the inside the box, that PCM will get solid. And during the latent heat absorption or latent heat release, the temperature of PCM remains constant. So there is no change in the PCM materials. That is the main advantage. So how much temperature? That we have to check. So during latent heat absorption, latent heat release, whenever it absorbs energy or release the energy, the entire PCM materials for the whole period, that will be at constant temperature. There is no increase in temperature. And this is the figure shows latent heat fusion or latent heat vaporization, right? And the x-axis it's given heat supplied, and y-axis is given temperature. When the phase changes from solid to liquid, that is latent heat fusion. The temperature remains constant when it turns from solid to liquid, right? That is latent heat. That horizontal line, the temperature will be constant. There is no increase in the temperature. Again, when the phase changes from liquid to gas, that is latent heat vaporization, right? Again, for small amount, the temperature will be constant. The temperature remains constant as liquid turns to gas. So these two portions maintains constant temperature. So these two portions are called latent heat. Solid to liquid means latent heat fusion, and liquid to gas, latent heat vaporization. And phase change will be at constant temperature, and this will absorb and emit heat while maintaining a nearly constant temperature, almost constant temperature, right? That is called latent heat. And this is how PCM works. And initially we have in the solid state, that blue color line, blue color core with shell, right? The outer surface is called shell, and in the inner side we have core. That some PCM material. So some PCM materials, it is in the solid state. When the temperature rises, when the demand, that means the temperature rises, that get melts. As the PCM melts, it absorbs heat energy. From this is the assume this is one cycle, right? So assume this is the starting position. When the temperature rises as the PCM melts, that means that absorbs energy. That means the inner core becomes in the liquid state. So initially that will be in the solid state. When the heat increases, when it's subject to some temperature rises, that will be in the liquid state. Again, when the temperature falls, what happens? So this core will become solid. That means that PCM solidifies and heat energy is released back to the environment, right? So initially the energy will be stored when the phase changes from solid to liquid, and the energy will be released when the phase changes from liquid to solid. Right, this is the concept of phase change materials, how the phase changes from solid to liquid or liquid to solid. So when the phase changes from one phase to another phase, what happens? So when the energy absorbs, when the energy releases, right? And this is the temperature effect, and we are dividing total process into two cycles: heating cycle and cooling cycle. When the heating cycle, as I said, the sensible heat, there is some increase or decrease in temperature, that's it. There is no latent heat in that. Latent heat means there is no phase change, and sensible heat means we have only increase in temperature, right? Then we are having latent heat, that is melting process. Then the material changes to liquid, that's a heating cycle. So after that, that is reverse process from liquid to solid. So sensible heat, then freezing process, that means the temperature decreases, automatically that gets into solid. This is the reverse process, we are getting cooling cycle, energy in heating and cooling. And how this PCM developed and when it is developed and why they have developed this PCM. And during 1970s, 70 to 80s, the NASA space research included the considerable research and development of new materials because that could protect delicate instruments in the space. That's the main reason why they have developed PCM. That's the need at that point from the temperature extremes they encountered. In 1987, Triangular RNG that demonstrated the feasibility of incorporating PCMs within some textile fibers, and that got patented in 1994. They started the process in 1987, that have patented in 1994. Here the PCM microcapsules within a fiber covers a broad range of fibers, including polyesters, nylon, acrylics, and monoacrylics. In the mid-1980s, the work on temperature-adaptable fabrics was undertaken at the US Department of Agriculture, Southern Regional Research Center in New Orleans. So this is starting of PCM. So when it developed, what is the reason? What's the demand? So there is some demand, and only we start some new process, right? So actually NASA, they required to safeguard their precision equipments, accurate equipments. For that, they are thinking, so that point they have developed this PCM, phase change materials. And this is small examples why we need phase change materials and what are the reason, right? If you take, this is the medications traveling. So we have to keep temperature 2 degrees Celsius to 8 degrees Celsius. And cefotaxime injection, we have to keep below 5 degrees Celsius. So we have to keep some constant temperature. And while traveling, how we can keep? So for that case, we are depending on this PCM materials. So this PCM materials will help a lot to maintain the temperature of these medications, because almost more amount of PCM materials they are using in the medical field to safeguard the life-saving injections, right? And the tetanus vaccine injection, if you take 4 degrees Celsius to 8 degrees Celsius, and the Rabipur, that is prevent rabies infection. So these are the few examples where we have to keep a constant temperature. So if you want to keep some constant temperature, we have to depend on PCM, phase change materials, while traveling. And this is the few examples where we are using this phase change materials. So transportation of blood samples from, if you want to transport from one place to another place, if there is no temperature, normal, some temperature, whatever temperature required for the blood, so it will get thicker, right? So we have to keep some constant temperature, then only the blood remains in the same state. Otherwise, the phase changes of the blood phase changes, then again that is useless. Then temperature control for transport for food and beverage industry, right? Then mini cold storage unit for ambulances. So ambulances almost they are using phase change materials to keep the ambulance temperature, right? They need some cold storage. They have to keep some medicines in the normal temperature. And storing of breast milk and feed infants with utmost care during traveling. So that also a main important thing. While traveling, we have to take care of children also. So these are the few places where we are using these PCM materials. And what are the properties of PCM materials? This is the general thing only. So on what basis we have to select, and what are the different properties of PCM materials? So these properties will change based on PCM materials. And melting point should be in the desired temperature range. That is the main point, right? So melting temperature we have to take it. Then only the constant temperature will be remains. And high latent heat of fusion per unit volume to store more amount of energy in a given volume. So high latent heat of fusion per unit volume, that also we have to take care. And high thermal conductivity. So that is also again an important factor. Important property of PCM, how much amount of thermal conductivity to assist charging, discharging of energy. And low change in volume. So high thermal conductivity and low changes in the volume during phase change, and low vapor pressure to avoid containment problems, and non-flammable, non-toxic, and that should be chemically stable. And apart from all, we have to, right, depend on cost, because cost also main problem. So low cost and low containment cost, and low vapor pressure at the operation. These are the few properties of PCM. So these are things we have to keep in mind. And we can divide the entire PCM like this: organic, inorganic, eutectic. And organic, we have paraffin compounds, non-paraffin compounds, and inorganic salt hydrate metallics. And the eutectic, this is the phase change: organic, organic, inorganic, inorganic, and then inorganic to organic. And small examples I'm giving. And inorganic salt hydrates, and maintains 5 degrees Celsius to 80 degrees Celsius. So examples of inorganic solids, salts, and high latent heat storage capacity, and fails to recrystallize. And paraffins, and it also has high thermal conductivity, and there is small change in the volume while melting. And paraffins, we are maintaining minus 80 degrees Celsius to 40 degrees Celsius, and overcomes supercooling and chemical stability over number of cycles, and varying cost and hazardous to skin. And bio-PCM, number of places they are using now, right? That maintaining between minus 40 degrees Celsius to 151 degrees Celsius, and from animal fats and plants. And we'll see about organic materials. This is the process possess the ability to absorb and release the large quantity of latent heat. That's the main advantage of organic materials. It absorbs and releases large quantity of latent heat during phase change process over a certain temperature. That is at the constant temperature. So this would be naturally existing petroleum byproducts: naphtha, gasoline, fuel oil, bitumen, and hexane. And it have their unique phase change temperature. And temperature range between minus 70 degrees Celsius to 250 degrees Celsius. This phase transition: solid to liquid and solid to solid phase transition. In the solid to solid phase transition, we have some crystalline changes, right? And one crystalline state to another crystalline state. There will be a small amount of latent heat. When there is a phase change between solid to liquid, that shows large amount of heat with a small volume change. Because we have to take care of how much amount of volume changes. If you take larger heat quantity storing with a small volume change, that will be better. Right? If the volume changes too much, again there will be a problem. And these are the classification of organic materials: paraffin material and non-paraffin materials, and paraffin wax, rubitherm, and dry granules. And about paraffin materials, it consists of mixture of mostly straight chain N alkanes, and the crystallization of methane chain release of large amount of latent heat. However, under cost consideration, only technical grade paraffin may be used in latent heat storage system. So only these are the standards we are using. So 6106, 5838, 6035, 649. These are the grades we are using. paraffinous Pcm materials. And these materials have phase change temperature below 15 degrees Celsius are used in cooling cycle. So when we use in cooling cycle, the temperature below 15 degrees Celsius. So another side, the temperature rise to 90 degrees Celsius. So PCM is in between 15 degrees Celsius to 90 degrees Celsius are used in heating cycles. And apart from that, the paraffin is very safe and we can rely on that, and it will be non-corrosive and less expensive, because cost is the main criteria for selecting the PCM, because remaining things also is important. So apart from that, cost also we have to take care, right? So if you compare, paraffin gives all the properties with the less cost. So almost we are dependent on paraffin for PCM materials in number of applications, and has low thermal conductivity and not compatible with plastic container, and it is flammable. So above three effects can be partially eliminated by modifying the wax and storage systems. So we can eliminate these undesirable properties. So by eliminating these three properties, the paraffin is entirely good PCM materials. On non-paraffin materials, this each and every non-paraffin materials have unique properties, and they should not be exposed to excessively high temperature. And these are the few properties of non-paraffin materials: high heat of fusion, varying level of toxicity, and instability at high temperature, and mild corrosive. So these are the few properties of non-paraffin materials. Then Eutectics, this we have studied in a phase change ion carbon diagram, right? So these are combination of two or more compounds and minimum melting temperature. This eutectic almost melts and freezes without phase separation. So that is the problem here. So without phase changing, without phase separation, it almost melts and freezes. And this eutectics tend to be a solution of salts in water that have a phase change below 0 degrees Celsius. And on what basis? Already we discussed what are the properties, and these are the things we have to take care while selecting a PCM materials. So again, number of things it is repeating again. So melting temperature, heat capacities, thermal stability, mechanical stability, cyclic property degradation, heat transfer characteristics, cost, corrosiveness, ozone depletion potential, fire hazard, ease of encapsulation. Right, so that is the main ease of encapsulation. So that also we have to take care while we are selecting the PC materials. So what application we are using, where, which place, what location we are using. So these things we have to take care, right? So these are the different applications of PCM. So apart from this, we have n number of applications. So latent heat battery. Normally, if you take our automobile's car, so the battery stores energy, right, from the radiator, and that will release energy in the cold for 2 or 3 days. If you not start our car for next 2 days, that will provide the energy, right? So that is this one kind of PCM materials, battery cell and latent heat cooling wrap around the battery. And heating in buildings. So to avoid too much of heat inside the room, we are doing coating, or we placing the PCM materials on the terrace, right? So if you place proper number of coatings, number of layers with the PCM materials, here they're given. So insulation, then thermal back on pipes, concrete, and floor covering. So if you do such kind of setup in the floor, right, the heat, whatever heat received from the sunlight will not feel inside the room. So the room temperature will be constant throughout the day. That's why we are doing this PCM insulation on the floor. And solar water heater, as you know, and cold storage and sportswear. Cold storage like normal flasks, how that's maintaining the temperature. For that we are using PCM materials. So that we are going to discuss today. And sportswear. The sportswear, why we are doing sportswear means that has to manage the temperature, right? Whatever heat generated from the body and the heat released to the environment, that should be balances. So otherwise, the too much of tiredness will get, right? The thermal stress will be reduced by using this PCM sportswear. That is the main reason why they are wearing like this, to balance the heat generated by the body and the environment. And how to incorporate this PCM, right, for any applications. And we can incorporate, we can immerse, and a third process is we can encapsulation. So here we have micro encapsulation, macro encapsulation. That means we can, by adding 2 or 3 chemicals, we can make a smaller balls, like, or we can make some new materials, right? And we can place wherever it required. This is the encapsulation morphology. And here we have two, and core and shell, right? So core is the inner side of shell, and that core only we are going to place, or in the region, in the hollow section, and the last multi-wall, wherever we have placed the hollow section, there we can place our PC materials. So those PC materials in the form of spherical, tubular, oval, or can be made in irregular shapes based on our applications. And this will be available in the form of powders and slurries. And this PCM with melting point from 10 degrees Celsius to 80 degrees Celsius can be micro encapsulated. The small video I'll share how we can make this encapsulation process. Yeah, this is visible, right? So these are the small things, whatever regular usage of all the things, almost regular usage, right? 4 tumblers, a volumetric flask of 200 ml, magnetic agitator, syringe, and needle, funnel. And here we are going to take 2 different materials. Sodium alginate solution. It'll take only 2 minutes, not more than that. And calcium chloride. This is the sodium alginate. That means how they are making phase change materials by adding 2 different materials. Because this also you should know, right? And calcium chloride solution. So these are the 2 different solutions we are in, sodium alginate and calcium chloride. By mixing these 2, the output, the final solution will be calcium alginate. So this calcium alginate will be mainly for wounds dressing. So when we get some wounds when dressing, so those places we are using this calcium alginate. Apart from this particular solution is used for entrapment of enzymes and forming artificial seeds in plant tissue culture. So how they are preparing microcapsules? Because as a PCM metal, we have to make some capsules like things or balls like things. Then only we can put those tubes or balls in the PCM material, that application, wherever, either flask or whatever it is. Here we can have the 2 categories, whether we can keep sodium alginate is constant and we can add calcium chloride, or in the calcium chloride we can add sodium alginate, smaller amounts. Will be small. If you look at the video, small balls are making by adding these things. How we are making phase change materials. So finally, we have got phase change materials in the form of balls. small amount. So these are the phase change materials. So this phase change materials we can use for any kind of applications where we need some constant temperature, right? Energy store and energy release process. So I'll stop this. So this is the video how we are, right? So this is the Pcm encapsulation morphology, how we can making the Pcm. And this is, we can keep calcium chloride stationary and we can move sodium alginate, or we can keep sodium alginate stationary, or we can move calcium chloride. So there is a small change, right? High irregular gel chip, less irregular gel chip. That is the, anyway we'll get only calcium alginate gel. That is the final result. There will be some irregular shape based on these two different phases, process. And this is the how we are making the Pcm encapsulation. And solid, when heating it makes to liquid, when cooling it again makes to solid. This is a small example how we can make Pcm for storage device. So phase change at constant temperature, and we have to observe and emit heat while maintaining nearly constant. So here I am taking SAVE OM03 as a Pcm material, and insulation material is polyurethane. And flask body, flask I'm going to make made of polylactic acid. And this is the technical specification of that material. And this is the insulation foam, and this is the polyurethane in the form of powders, right? And this is the flask we made, and this consists of totally 3 parts: body, removable seal, and the cap. And the body is a 3-walled concentric cylinder. Here we have on the bottom we have insulation, Pcm, and low temperature product. These are 3 layers. So innermost hollow cylinder, that's low temperature product. Middle cylinder we are using for Pcm, and outermost cylinder we are insulating. So these are 3 layers. So how we are going to place the Pcm, and what type of Pcm we are going to place. There is the design. And this is the standards we are taking from Yoram Kozak, and we assume these things. The process is quasi-static. That means we are quasi-static, quasi-steady process, right? That means we have to, this is one kind of thermodynamic process that happens slowly enough for the system to remain in internal equilibrium. That is the main thing. So that should be in equilibrium. That is quasi-steady state. The solid Pcm temperature remains at the melting temperature. The material properties, heat transfer coefficients to the ambient and the ambient temperature are constant. So these are some assumptions we took while making model of that flask. And this is the relation between the thickness of insulation, thickness of Pcm. So what's the thickness of insulation? And what's the thickness of Pcm materials we placed, and how much time taken for melting the Pcm. So we made these 3 relations by using this graph. And like this way we insulated, right? Polyurethane insulation filled in the outer layer. This is the outer layer. So here we filled with the polyurethane. And this is the polystyrene tubes we have taken initially to check, because we have to keep this, sorry. Right, so initially we have taken polystyrene tubes, and this Pcm is freezed after 48 hours and made solid form, whereas immediately that will be broken due to the material compatibility. So we have not used this, and we selected polypropylene. This is sterilized at 120 degrees Celsius, and this is almost compatible with almost all the materials. So here the compatibility possibilities are given. So almost it's compatible with all the materials. So we have taken this, and this is the Pcm SAVE E OM03 external fine its application chilled product transportation. This is the PCM materials we have used in the polypropylene tubes. And like this way, we made after the freezing temperature, the frozen PCM tubes kept inside the flask. So this is the flask and these are the PCM tubes we kept. And we did some study on that. When the heat converted, the trials were taken with water to get converted from 2 degrees Celsius to 15 degrees Celsius. And these are the results we got. So without PCM, this is the temperature range, 2 degrees Celsius to 15 degrees Celsius. Without PCM, it holds only 3 hours to 22 minutes. With PCM, that holds more than 1 hour. So 4 hours, 34 minutes, like this second sample, 3 hours, 10 minutes, 5 hours, 2 minutes. On average, we have taken 3 hours, 15 minutes without PCM and 4 hours, 46 minutes with PCM. So that is the reason why we are choosing PCM, right? And kind of PCM also is important. And the medical devices, medical field. So that is the normal cold storage, right? Cold storage device. That is flask. Flask we are taking and we are filled with some PCM materials. So PCM materials also given some good results that because that holds more than 20% of previous temperature. 20% time it holds the cooling effects, right? That's why we are going with PCM materials. So this is small medical applications based neonatal cooling devices. When almost a number of hospitals they are using, one second. So number of hospitals they are using this phase change materials. So especially this SAVE FS21 and SAVE FS29. This I have taken from neonat cooler. And for precise temperature control cascade system of PCM is used. Quasi-automated cooling system is created. So here we have a number of layers to make the baby's body cool. Because in the top floor we have conduction mattress. So there only we place our babies. And the temperature, we have to maintain some constant temperature, right? Otherwise some sore will face by the babies. This passive heating and cooling substances usually made of a salt hydride, fatty acid, and ester or paraffin such as AICTE. And these phase change materials are solid at room temperature normally, right? But when it contact with the warmer objects, they liquefy and absorb and store heat. When the temperature increases, automatically the phase changes from solid to liquid and it absorbs energy and that will store. And liquid PCMs can solidify and give off heat. Once it is stored in refrigerator for 6 to 8 hours, it can be used up to for 72 hours without uninterrupted power. So that is the reason why we are using, already I said, right, for transportation of medications. For life-saving medications, we are using these phase change metals to maintain the constant temperature. And here, if you use proper refrigerator by using this kind of PCM materials, for 72 hours without any power, we can have a normal temperature. We can maintain the temperature in the baby's beds. So that's why we are going for this kind of PCM materials. So this is the 4 layers we have. And the bottom we have the insulated cradle to keep all these layers. This is a plastic structure framework for placing all the other components and provides insulation to the PCM. Yeah, this only provides insulation. Insulation means we have to insulate with the outer cover, outer surface of the PC materials. So this provides insulation to the PC materials. And bottom layer on the top bottom in solid state passively extracts heat from the neonat's body, which is at 37 degrees Celsius. And this will inducing and sustaining hypothermia, right? Then the middle layer. So this is the middle layer, bottom layer. Middle layer, it used the conjunction with the SAVE FS29 PCM. Quickly bring the temperature of the neonat down to 33 degrees Celsius. So bottom layer, we have 37 degrees Celsius, and this middle layer brings to 33 degrees Celsius. And the conduction matrix is, this is at the top, where we are placing our babies, right? It's a gel bed, which provides a smooth surface for the baby to lie on. right? That improves the heat transfer between the baby and the PCM. So that conduction matrices that only transfers the heat from baby to the PCM or PCM to the, that means we have to keep some constant temperature without getting any sore on the body. We have to, then only, otherwise the again the problem, right? The baby will face another kind of problem because of this sore. And this is the neonatal cooling device, which is in the use in almost number of hospitals. They are using this neonatal cooler, because for this kind of beds we have to keep babies a number of days, number of hours. For that we have to keep proper PCM materials. And this is the advantage of this neonatal by using these different materials. So cost almost 1/10 of the existing equipment, because the PCM materials, if used properly, the temperature for 72 hours, it maintains the temperature, right? So automatically the cost of the entire system gets reduced. Another advantage why we are why the cost is reduced means all the PCMs will be reusable and there is no maintenance cost. That's the main thing. So the same PCMs we can reuse and no need of such maintenance, and does not require any electricity when in use. That's why it keeps the temperature right for next few days. So we no need of electricity and no intimidating wires and circuits for the nurses and doctors. So because the already baby lies safely on the this kind of PCM beds, so no need to worry about what's the no need to worry about remaining things, right? So no intimidating wires or circuits required for the nurses or doctors who keep this baby safe. So with this, I'm closing my presentation. So thank you all for your participation. If you have any queries, we can ask for next few minutes. Thank you. Thank you all for the kind participation. Shanmugam sir.
Hello, Mani sir.
Yeah.
Yeah, Mani sir. Okay.
So my presentation is over.
Okay.
If you have anything to.
Okay, sir. Yeah, thank you very much, sir. Thank you for your wonderful session.
Thank you.
If participant, if you are having any specific queries, kindly post your queries in the chat box, or else you go to unmute yourself and ask the questions to our expert member.
Put in the chat box.
Good morning, Pa.
உங்க வாய்ஸ் ரொம்ப கம்மியா இருக்குன்னு நினைக்கிறேன். இல்ல என்னோட வாய்ஸ் நிறைய இருக்கா?
Voice, okay.
10 o'clock class.
கேக்குதா சார்?
10 o'clock class. Good morning, good morning. 10 o'clock class இருந்ததா?
வேற யாரோ பேசிட்டு இருக்காங்க.
ஓகே, எப்படி போயிட்டு இருக்கு கிளாஸ் எல்லாம்?
ஓகே.
சார் மியூட் பண்ணுங்க.
நம்ம கிளாஸ் எப்படி போகுது அத சொல்லுங்க.
கோபிநாத்.
Okay.
One thing is PCM used in regeneration of heat heat extrude transfer the heat from, because already due to some temperature change that will store some energy, and whenever it occurs that will releases. So main purpose of PCM is only for that.
Thank you, Mani sir. உங்க வீடியோ ஆன் பண்ணிக்கோங்க சார்.
Yeah, I'll stop share
Okay,
this.
sir. Okay, sir. Thank you,
Really
sir.
picture. ஒரு நிமிஷம். Yeah, now it's visible, right?
Yeah, yes, sir. Yes, sir. Yes, sir.
Yeah.
Thank you, Dr.N.Mani sir.
Thank you.
Any participant having any queries? Okay. Thank you, Mani sir. Thank you, sir.
Thank you, sir. Thank you.
Thank you very
Thanks
much.
a lot.
Thank you very much for your wonderful section today. We hope all the participants got benefited towards application of phase changing materials and also phase changing materials theory. Okay. Thank you very much for all present here. I think our second section guest also already joined.
Oh.
Yeah, Mailwell Nathan. Mani sir,
Okay.
Mailwell Nathan sir.
Oh, is there on the line?
Yeah, Mailwell.
Good morning, everyone, sir.
Yeah, good morning, sir. Good morning, sir. How are you,
Good morning, sir.
Fine, sir.
Yeah, thank you very much, sir. Here we have Dr.N.Mani sir from Sairam Engineering College. He
Okay,
only handled the first section.
It's a nice presentation, sir. I also
Yeah.
watched.
Thank you very much, sir. Thank you, sir. Mailway Nathan, he's also joined. Sir, can I continue, sir? Can I continue?
Sure, sir. Sure, sir.
Okay.
Sir,
Thank you, Mani sir.
Can I
Yeah.
leave? Yeah. Thank
Yeah,
you.
thank
Thanks
you,
all
thank you.
for
Thank
the
you, Mani,
opportunity.
sir.
Yeah. Thank you.
Yeah, thank you, Mani sir. Thank you, thank you. Yeah, good morning, participant. Morning section, we attended wonderful two sections morning. From morning 7 to 8, we attended yoga section, the meditation class. And today, at 10 o'clock, 10 a.m. to 11 a.m., we already gone through the PCM material sections delivered by Dr.N.Mani from Sairam Engineering College professor. And we are having another eminent personality, Mailway Nathan sir, from professor. He is a professor from, please. Muhammad Sadak Engineering College, Keelakarai. Welcome, sir. Welcome you, sir. On behalf of Sairam Institute of Technology, on behalf of management, Principal Dr. K. Palanikumar, and myself, Dr. G. Shanmugh, Associate Professor, Department of Mechanical Engineering. I welcome you for our AICTE STP online webinar, sir. Thank you very much. Thank you for your acceptance of our invitation and came over here and willing to deliver the lecture series. And Dr. Mailway Nathan is here. He is a professor and head Department of Mechanical Engineering, Muhammad Sadat Engineering College, Keelakarai. He has vast experience in teaching, total 20 years of teaching experience, more than 120 papers published in the reputed journals and the conferences he attended many. And he has a lot of experience in teaching, and also he is very familiar and well-versed in specialized in thermal areas. He is a specialist in thermal man. Okay, thank you very much, sir. Thank you for came over here and deliver the welcome address. Sorry. Thank you very much, sir. Thank you, sir. I hand over this section to our professor, Mailwell Nathan. Thank you very much, sir.
Thank you for your wonderful introduction, sir. Thank you, sir. Good morning, everyone. First, I must thank management, principal, and the organizing team of Sri Sairam Institute of Technology for arranging wonderful opportunity to deliver lecture in STTP program. Today, we are going to discuss about the topic phase change material for high temperature thermal energy storage in industries. I will share my screen.
Just a minute, sir. I make your. Yeah, yes, you can, sir. You can now.
So wait a minute, sir. So it is visible.
Yeah, yes. Yeah, it's not visible, sir. Your PPT.
Presentation is not visible.
Yeah, not visible, sir.
Okay. Share screen. I hope it's there. Okay.
That screen option is enabled, right, sir?
Yes, sir. Yes, sir. Enable, sir.
Okay, okay. It will come, sir. It will come.
Okay. Okay.
Yeah, it's visible, visible.
Okay. Outline of my presentation is to having two parts. The first part we are going to discuss about the need for energy storage, thermal energy storage, latent heat thermal energy storage, and materials, enhancement techniques, and applications. Then characterization studies, displacement experiment, characterization technique like SEM, DSC, FDR, XRD, thermal conductivity, etc., and like a thermal cycling test. The experimental studies like melting and solidification rate of NTPCM. NTPCM means it's a novel PCM. It's a nano dispersed phase change material. Effect of heat transfer oil flow rate and inlet temperature, overall heat transfer coefficient, heat flow rate, efficiency, and effectiveness. Then second part of my lecture going to deliver about high temperature PCM in industries like solar thermal application and industrial process heat application. The need for energy storage. The energy is an important for social, economic, industrial, and technological development of our country. In increasing energy demand, the decreasing conventional energy sources pushes the world to exploit new and renewable energy sources and to store energy in every possible means. To bridge the large gap between energy supply and energy demand, the concept of effective energy storage has been gained momentum in recent years. The electricity produced 2018 to 19 is a 900 to 1000 terawatt per hour. More renewable energy and less fossil fuel. Concentration of CO2 increases massively due to industrialization. Increased ratio of renewable generation demands energy storage due to high intermediate nature. The energy storage. The energy storage is an extensive subject of interest to industrial professionals, scientists, engineers, and technologists. The significance of energy storage is meet the flexible requirements, fulfill the energy demand, reduce the alternate power sources, produce safe energy and less carbon footprint, increase the overall performance of the system. The energy storage have four major classifications. These are mechanical energy storage, electrical energy storage, chemical energy storage, and then thermal energy storage. Then heat transfer mechanism in thermal energy storage system. Thermal energy storage system can store heat or cold to be used later under varying conditions such as temperature, place, it may be power. In main use of thermal energy storage system is to overcome the mismatch between energy generation and energy use. It involves three steps: charge, storage, and then discharge, giving a complete storage cycle. The classification of thermal energy storage system. Now, let us discuss about the types of thermal energy storage system. Basically, thermal energy storage system can be divided into three parts. One is called sensible heat storage, under which solid and liquid material can work. This latent heat storage, either it may be a combination of solid gas, solid liquid, liquid gas, or it may be solid or solid solid. Then solid liquid further classified into organic PCM, inorganic PCM, and eutectic PCM. And the third one is thermochemical energy storage. Either it may be solid gas or liquid gas or gas phase. This is the overall type of thermal energy storage system. How so here some examples of thermal energy storage methods are explained. Sensible heat can be stored by hot water tank or underground thermal energy storage tank. The thermal energy can be stored as a latent heat by means of micro encapsulation or macro encapsulation of phase-change material, or using latent heat thermal energy storage materials. Thermal energy can be stored thermochemically. It's by means of adsorption or absorption, or it may be thermochemical materials. Now, what do you mean by sensible heat storage? In sensible heat storage, thermal energy is stored based on the specific heat of the material. Whatever materials we are going to choose, that should have higher specific heat capacity. That is the prime requirement, what material we are going to use in sensible heat storage. Here, the temperature of the material varies and does not undergo any phase transformation during charging and discharging cycles. The amount of energy stored is given by Q is equal to integral of T1 to T2 mCp Tt equal to, finally we can get mCAS T2 minus T1. The T1 is the initial temperature of H2O, and T2 is the final temperature of the storage medium. CAS is the average specific heat between T1 and T2. The heat storage depends upon the amount of, in sensible heat storage, the amount of the heat and the energy storage depends upon the amount of storage material, specific heat of medium, and the difference between the initial and the final temperature. Second one is called latent heat storage. In latent heat storage, the process of storing and releasing the thermal energy is based upon the latent heat of fusion, where the storage medium undergoes phase transformation. Now we need certain material which will change the characteristics between T1 to T2. Best example is water. We know we have a freezing of water, it is in solid phase. Then it comes to the room temperature, it comes to a liquid phase. Then we are rising the temperature, it going to gaseous state. That means the for different temperature, the water becomes a different phase. One phase it is solid, one phase it is liquid, and one phase is a gas. As the source temperature increases, the chemical bonds of the phase change material breaks up, which leads to a transformation from one phase to another. Thus, in solid stage of water, it's having a crystal structure. In gaseous stage, liquid stage, it isn't. There is no crystal structure of water. In gaseous stage, the atoms are freely moved, so there is no structure in that organized structure of water. Energy stored in latent heat storage system is given by Q is equal to integral of T1 to Tm mCp Tt m into Am delta Thm plus integral of Tm to T2 mCp Tt. This is a formula to find out the latent heat storage system. Q is a quantity of heat stored. T1 is the initial temperature. T2 is the final temperature. Tm is the melting temperature of the storage medium. The delta Hm is the latent heat. The phase transmission of material can be solid-solid, or it may be a solid-liquid, or it may be a liquid-gas transformations. Next one, we will discuss about the thermochemical energy storage. The energy can stored in a chemical reaction which can occur in both forward and reverse direction. Endothermic reaction, energy can be used to form a product. It's an endothermic reaction. Energy stored in a product can be regained by exothermic reaction under specific conditions. Thermochemical energy can be roughly presented as the following sequence. These are the heat plus chemical compound A plus B is equal to gives C plus D. It's an endothermic process. Then the reactants can store the storage division. Reactants can store thermo energy for a long duration. Next one is a discharging process. It's an exothermic process. C plus D. C plus D is equal to CD plus some energy discharged. This is the fundamental of thermochemical energy storage. Then we will discuss about sensible heat storage materials. Sensible heat storage material should have higher thermal capacity, high melting point, high thermal conductivity, and high stability, the chemical and physical stability, thermal stability also, low cost. That should be in low cost. Commonly used sensible heat storage materials are concrete, cast iron, bricks are used for a temperature range of 400 to 1200 degree Celsius. The advantage of solid storage materials are low cost, no boiling point. The next one, liquid storage media. Liquid storage sensible heat media among the liquid water is the best for among the liquid. The water is the best for most commonly used storage medium at a low temperature range. The range is 25 to 90 degrees Celsius. We can use other substitutes for water are petroleum based oils, liquid sodium, and molten salts, etc. Heat transfer mechanism in latent heat thermal energy storage system. During charging process, when the PCM at solid state is heated, its temperature increases until it reaches the phase change point. Over this temperature range, heat is stored in sensible form. Further heating of material incurs solid to liquid phase transition, and heat is stored in latent form while maintaining constant temperature during this period. Once the phase change process is completed, the PCM is liquid phase. This reverse the process if the reverse the process and release the heat, which is also called discharging process or solidification process. The schematic summary of the properties of PCM. The property thermal, first we will discuss about the thermal physical property. The melting and solidification temperature of PCM in the range of desired operating temperature condition. A latent heat of fusion higher with respect to unit volume compared with the sensible heat. Specific heat and thermal conductivity in solid and liquid phase that must higher for enhancing heat transfer. And then kinetic properties. The kinetic properties relatively low supercooling or nil supercooling exhibited by the PCM. Then the chemical properties, chemical and thermal stability to withstand heat at elevated temperatures. No toxic, no flammable, as a non-flammable, non-explosive. The economic aspects are includes ease of availability, then commercially available, the cost effective, wide range of applications. Then organic material. Organic, the latent heat storage material can be divided into three parts. One is organic material, another one is an inorganic material, another one is an eutectic materials. Organic materials divided into two parts. One is paraffin, another paraffin, that's mean wax-based PCM. Another one is a non-paraffin PCM. So what is organic? A phase change material which contains carbon atoms is known as organic PCM. Organic PCMs are available for wide range of temperature which is stable till 300 degrees Celsius. Examples: paraffin wax, polyglycol, erythritol, etc. Now, what are the advantages of using this type of material? Because this kind of materials are freeze without much supercooling or subcooling. Ability to incorporate it directly. Low water pressure in phase change process. Good thermal performance. Ability to melt concurrently. Self-nucleating properties. Availability in large temperature range. No segregation. Chemically stable. High heat of fusion. But of course, it having some disadvantages also. Low thermal conductivity in the solid state. Some are insoluble in water. Low phase change enthalpy. Low density. Require large surface area. High heat transfer rate are required during the freezing cycle. Volumetric latent heat storage capacity is low. More expensive. High volumetric expansion. Low heat capacity. These are the disadvantages of organic PCMs. Then inorganic PCMs. The inorganic PCMs, inorganic PCMs are material which consist of salt hydrates, nitrates, and metals. Inorganic PCMs are also used for high temperature up to 1500 degrees Celsius. Examples: sodium nitrate, sodium chloride, magnesium bromide, potassium nitrate, etc. These are all materials. For example, in organic materials having certain advantages, there is a high thermal conductivity, large heat storage capacity, lower volumetric expansion, high heat of fusion per unit volume, less costly, non-flammable, short phase change, greater phase change enthalpy, and recyclable. And of course, it having some disadvantages also. High degree of supercooling, lack of thermal stability, phase segregation, incurrent melting and dehydration during thermal cycling. Some have a high weight, corrosive, chemical instability, requires container and support. Next, we will discuss about the eutectic PCM. Eutectic PCM is a mixture of two or more components at a particular percentage of composition. So the components can be any combination of like organic, inorganic, or inorganic, organic. This type of PCM melted freeze concurrently without any segregation. Similarly, during melting, different compound melt simultaneously, which also give less probability of compound separation. The material having certain advantages, which are short melting temperature, high volumetric thermal storage density, no phase segregation and concurrent phase change. Of course, it having some disadvantage also, lack of current availability test data, thermophysical properties, low total heat capacity. Some eutectics suffer from supercooling effect, strong order, costly. Here this is a scatter diagram for high temperature PCM. The figure shows the latent heat enthalpy for different type of high temperature phase PCM materials at a different melting temperature. It contains sugar alcohols, which contains erythritol and mannitol. Organic materials, which includes polyethylene, then molten single salt. It contains lithium nitrate, sodium nitrate, potassium nitrate, metals, which contains zinc. 18. The melting point and enthalpy of PCMs. The suitable PCM can be found for wide range of operating temperature. Then comparison of sensible, latent, and chemical thermal energy storage. Among this different type of thermal energy storage, latent heat storage has most flexible of operating temperature range, followed by the considerably lower operating temperature ranges for sensible and thermal chemical storage. The advantage of using latent heat over sensible heat storage technology is that it has 10 times higher thermal energy storage density, a capacity of 50 to 150, and around trip efficiency of 75 to 96%. Latent heat storage. Normally, PCM having less thermal conductivity and a less heat enthalpy. In order to enhance the performance of the latent heat thermal energy storage, the following techniques are used. First one, adding nano and metal additive to the base PCM, which will enhance the thermal conductivity and the heat transfer rate of the PCM. Next method is to encapsulation, then using soaked material and a safe stabilization of PCM. The latent heats, the thermal energy storage, are used to heat applications like solar thermal applications, process heat and waste heat recovery, photovoltaic thermal applications, internal heat gain for passive applications. The cooling applications like insulation, then ventilation and evaporative cooling like that. These are figure use displays the set of applications of PCM. Using PCMs to store energy is an effective method to improve the efficiency of the system due to its isothermal nature. Solar energy, the solar air heating system or solar water system. In building applications, passive and active technology. In cooling, the solar cooling and thermoelectric refrigeration. In heating application, hot water system and heat exchanger material. Then solar power plants, concentrated solar power plant. food industry, super chilling of food processing, then spacecraft thermal control. Then characterization and thermophysical property of NDPCM. The preparation of a novel class of nanoparticle dispersed PCM by dispersing graphene nanoparticle with the three different mass fraction in erythritol PCM is presented. The thermophysical properties and the characterization of a novel PCM were analyzed, and enhancement in heat transfer properties of NDPCM is reported, and the results are summarized in next slides. The higher thermal conductivity of PCM, the erythritol, is selected for listed PCM. Erythritol most used in food industries. It has high density of 1480 kilogram per meter cube, and it allows a large quantity of erythritol to be packed into the small volume. Because of high melting, it can be used to absorption chiller, steam generator, industrial waste heat recovery, and solar cookers. The nanoparticle should have higher possible thermal conductivity. Carbon-based nanoparticle can be directly used to enhance the thermal conductivity and stability of PCM. A graphene is two-dimensional honeycomb structure, one atom thick, emerging as a suitable for latent heat thermal energy storage system because high thermal conductivity, high surface area, maximum chemical stability. The distribution of carbon atoms in graphene nanoparticle in both centrosymmetric and axisymmetric. These are some thermophysical properties of the erythritol and graphene. Then disbursement experiment. Graphene dispersed erythritol PCM was prepared by two-step method. The erythritol was melted approximately at 120 degrees Celsius by hot plate and then poured into the beaker. The beaker was kept at an ultrasonic vibrator for 2 hours. A certain amount of GNP, that's graphene nanoparticle, 0.1%, 0.5%, and 1% was added with the molten PCM. The ultrasonic temperature was about 140 degrees Celsius to ensure the samples kept sufficient above the melting temperature of the erythritol. These are the prepared samples of the characterization techniques. The PCM characterization techniques can be classified in two types. One is a thermal characterization, another one is a chemical characterization. The thermal characterization includes study of phasing material, latent heat, thermal conductivity, and thermal stability. Chemical characterization studies includes to find the size, shape, and the crystalline structure. Chemical characterization technique, the surface morphology of PCM or NTPCM, the microstructure or morphology of erythritol with oil, morphology and the microstructure of the erythritol with a 0.1%, 0.5%, and 1% graphene samples were investigated by field emission scanning electron microscopic analysis. The size of the nanoparticle is in samples have found to be 28 nanometer to 35.8 nanometer. Some images showed that the graphene nanoparticle randomly distributed and hold the nanoparticle in fixed positions. Chemical stability analysis of NTPCM. The Fourier transform infrared spectra was measured in a range varying from 4000 centimeter minus 41 equal to 400 centimeter per minus 1. These observed FTR results suggest that there is no chemical reaction between erythritol and the graphene, as the change in all peaks between pure erythritol and graphene added erythritol is negligible. X-ray diffraction spectra are pure erythritol and erythritol with 1% GNP shown in figure. The crystal structure was calculated to be 35 nanometer and the latest strain was 0.0062 for pure erythritol. It can be concluded that all the addition of graphene to erythritol NDPCM has peaks intensity that was approximately similar to erythritol, and it indicates graphene produced no crystal change in erythritol. Then thermal characterization techniques. Differential scanning calorimetry (DSC) was used to determine the latent heat and phase change temperature of melting and freezing of PCM and NTPCM. Here, so the DSC diagram already taken. Then thermal characterization techniques, so thermal stability test or thermal cycling test. Thermal cycle test uses to know the long-term stability of the storage material. The thermal cycling system was designed to operate between 30 degrees Celsius and 140 degrees Celsius. Totally 1000 cycles were taken. Each cycle contained one melting and one freezing process. These are the physical state of the PCM and the NDPCM samples during the melting and solidification process, shown in figure. Next, thermal conductivity. The figure shows the different methods to find out the thermal conductivity of at a transient and steady state conditions. In the transient condition includes hot wire method, thermocouple method, TPS method, LFI method, and TSC. Then a steady state method includes corded plate method and heat flow meter method. The thermal conductivity LFI method. Now we are using in our research, we are using LFI method. Thermal conductivity of PCM, NTPCM can be calculated by LFI method. The thermal conductivity of erythritol was enhanced with the increase in weight fraction of GNP due to its high thermal conductivity. Thermal conductivity of erythritol is 0.733 watt per meter square Kelvin. Due to its addition of 1% GNP or graphene with the erythritol lead to 53% increase in the thermal conductivity. Then experimental investigation. Detailed experimental investigation was conducted to analyze the effect of various inlet temperature and mass rate of terminal as a heat transfer oil on the rate of melting and solidification of base PCM erythritol and NTPCM in horizontal shell and helical tube latent heat thermal energy storage system, and results are compared in next slides. These are the heat storage material and heat transfer oil we are using. This is a design of the photographic. This is a design of helical coil heat exchanger. It is a heat storage medium here. This is an experimental setup. The photographic view of the experimental setup used in the current research work shown in figure. It consists of heat exchanger, high temperature path, low temperature path, circulation air pump, K-type thermocouple, data acquisition unit, and necessary pumping systems. The heat storage container consists of tube surrounded by heat storage material. It's a photographic view of helical coil tube. Here we are using 20 number of K-type thermocouples with a measuring range of 0 to 270 degrees Celsius, located axial direction. Two thermocouples were placed at the inlet and outlet of the tube. As a schematic experimental setup used for charging and discharging experiment, 88.5 kilogram of heat storage materials was loaded in the heat storage system. In one thermal cycle consists of one complete melting and one solidification for PCM and NTPCM. The melting time of NTPCM was reduced by 22% as compared with erythritol. The solidification time of NTPCM was decreased by 23% as compared with the pure erythritol. The next slide, effect of heat transfer oil inlet temperature. The melting time was reduced by 19% for pure PCM and about 21% for NTPCM when the heat transfer oil inlet temperature was increased from 160 degrees Celsius to 180 degrees Celsius. The solidification time was reduced by 10% for PCM and 14% for NTPCM when the heat transfer oil temperature was decreased from 45 degrees centigrade to 30 degrees Celsius. The next one, the effect of heat transfer oil flow rate. Melting time was decreased to 20% for PCM and 30% for NTPCM when the flow rate increased from 0.5 kg per minute to 2 kg per minute. The certification time reduced by 19% for PCM and 20% for NTPCM when the flow rate increased from 0.5 to 2 kg per minute. Then performance investigation we have done. The overall heat transfer coefficient T1 during melting process, the overall heat transfer coefficient increased 7% during melting process and 6% during solidification process. Then heat flow rate. The beginning of melting process, heat flow from heat transfer oil to phase change material increased by 3%, and for heat transfer oil to the nano dispersed phase change material is 4% for 5 degrees increase in inlet temperature. Beginning of solidification process, heat flow from phase change materials to heat transfer oil increases by 4% and nano dispersed PCM to PCM by 7%. Then efficiency. The charging efficiency of the system was increased by 32.89% for PCM and 42.87% for NTPCM. The discharging efficiency of the system was 38.25 for PCM and 55.08 for NTPCM. The phase change efficiency of the NTPCM is higher than the PCM, which is due to the dispersion of graphene nanoparticle in the erythritol. Next, we are going to discuss about the effectiveness. What are the effectiveness in the latent heat thermal energy storage system? The effectiveness decreases with increase in mass rate of the H2O. The increase of mass rate involves the reduction of H2O temperature difference, reduction of H2O temperature difference between the inlet and outlet. Hence, the effectiveness decreases. In melting process, the effectiveness of NTPCM was 14%, greater than PCM. In solidification process, effectiveness of NTPCM was 12% greater than the base PCM. Yeah, okay. We'll come to the second part of our presentation. It's a high temperature PCM in industrial applications. Percentage of heat demand in industrial sector. The report showed that 30% of industrial heat demand is below 100 degrees Celsius, 27 is in medium temperature, 100 to 400 degrees Celsius, and 47% is in high temperature applications. International Energy Association, Solar Heat and Cooling fixed the industrial heat demand at a medium temperature 100 to 400 degrees Celsius in 19% of total heat demand. This demand can be solved by utilization of waste heat recovery from industries. It is essential to store the excess energy, and the energy stored can be recovered and reused when it's required. Then selection of high temperature phasing material. The figure explains the relationship between the performance of the heat storage device and the properties of heat storage materials, and also show that above two of influence the one another. A summary of thermophysical properties of some excellent high temperature molten salts and commercially available PCM which are used in industrial applications. Pure inorganic salts. For high temperature applications, inorganic salts have subjected to a great interest. As a range of melting temperature from 253 degrees Celsius for pure lithium nitrate to high temperature of 1580 degrees Celsius for pure lithium sulfate. The mixture of different salt allows to reduction in melting point. For example, fluorides and their mixtures. The melting point of the sodium nitrate can be decreased by mixing it with the other salts like sodium hydroxide but the latent heat of the fusion mixture is increases. In this slide, I want to show some video about solar thermal power plant incorporated with a thermal storage system.
Sir, the video is not coming, sir.
Sir?
Why, sir? Video வரலையே, வெறும் empty screen மட்டும் தான் இருக்கு.
Okay, sir, I will show.
Okay. Solar thermal power plant with energy storage system title தெரியுது.
Yes, sir.
அந்த black screen மட்டும் தெரியுது. வீடியோ லிங்க் ஆகல சார்.
Oh, sorry. Okay, sir. Sir?
இல்ல வரல.
Oh.
black screen மட்டும் விசிபிளா இருக்கு சார். செப்பரேட்டா ப்ளே பண்ண முடியுமான்னு பாருங்க சார். இல்ல ஆல் அதர்வைஸ் கோ ahead sir. No issue.
Okay, sir.
Okay.
Sir, next screen is over.
Yeah, visible sir. Direct absorption based solar.
Yes, sir. Direct absorption based. Okay, direct absorption based solar collectors working with a high temperature heat storage material. This system with a parabolic trough collector to provide intensive heat for many industrial processes such as electric power plant, absorption refrigeration systems. The charged nanofluid can transfer heat to the Pcm to ensure the stable heat supply. Here, this system having parabolic trough collector is a heat source. Then is combined with the power plant and solar power plant and absorption refrigeration systems. In between that, we are providing some thermal storage system to maintain the thermal stability of the overall systems. Direct active two-tank thermal storage system. We are using solar salt used as a facing material. 60% nano sodium nitrate and 40% potassium nitrates are used as a solar salt are used as a PCM. Hot and cold fluids are stored separately. No additional heat exchangers are used. Fast heat transfer process taking place for freezing of salts. 120 to 220 degrees Celsius. Auxiliary heater is required to maintain the temperature above freezing during the night time. Then next one is a indirect active single tank thermal storage system. Hot and cold fluids are stored in a single tank. Hot and cold tanks are separated because of the certification effect. Controlled charging and discharging are necessary to maintain the certification. Then industrial applications. The heat transportation container using high temperature facing materials. The heat transportation container using high temperature PCM. Schematic diagram of the trans heat system using PCM and heat transport container. There is an industry here. the waste heat is available for produced here, then the heat is transferred from the industry to the city by this mobile transport system. Mobile transport system they are using. Then the direct or indirect contact storage container, mobilized thermal energy storage system. And this also mobilized thermal energy storage has developed to receiver industrial waste or excess heat for distributed uses. The direct contact storage container active shorter charging or discharging process for the indirect contact area. Sir. Yes, sir. Okay, thank you for listening, sir.
Yeah, thank you.
Any queries, sir?
Thank you very much, sir. Thank you, sir.
I have some videos, sir, but I can't play it. Sorry.
The video separately, you can separately it will open, sir, right?
Okay, sir. I will send
Yeah, close.
PPT also.
Or else you have to close this
No problem,
PPT.
sir. Okay, sir. No problem, sir. No problem.
Okay.
I will send a PPT.
Okay, sir. Thank you, sir.
Any
Thank
queries,
you.
sir?
Thank you, Mailvendra, sir. Thank you very much. I request all participants, if you are having specific queries about this section or any topic, kindly interact with our guest or post it in the chat box.
Hello.
Yeah.
Tell me, sir.
Hello.
Yeah, yes, sir.
Yes, sir. I hear, sir.
Yeah, here. Yeah. Yeah, kindly
Hello.
ask your question, sir. Yeah, yes. Yes, kindly ask your question,
Is
sir.
it possible to disperse the nanoparticle? Hello. Is it
Yeah, yes,
audible?
It's audible, sir.
Is it possible to disperse the nanoparticles evenly in the PCM, and what is the methodology? Is there any precautionary measure you have to take in order to disperse the particles?
Yeah, sir. Hello. We are dispersing the particle. That is
Hello.
a storage container only. It can't
Yeah.
move. It can't move.
How to ensure?
It can't move. It's not a direct contact. It's an indirect contact only. Over the tube, the PCM are stored. Okay, that's all.
Okay, thank you.
Okay. Any other questions from participants?
Anything more?
So there is one more question.
Tell me, sir.
Sir?
Tell me, sir.
Why did you choose graphene percentage as low volume?
Sir, this is cost effective because of it's a very much cost. Hello. Within 1%, we can get the higher the thermal conductivity enhancement. The 53% we get from 1%. So no need to increase the percentage of addition.
Sir, okay, sir. Okay, sir. Thank you very much, sir. Thank you, sir.
Thank you, Shanmugh sir. And,
Yeah, thank you. Thank you, sir.
sir.
Thank you, sir.
One more question.
Yeah, one more question.
Tell me.
So from the participant,
Okay,
is it possible to mix the nanoparticles in PCM by ultrasonication?
Yes, sir. Yes, sir. True, sir.
Nanoparticles.
Ultrasonication is possible. Preparation method.
Okay.
We can do it. We can do it, sir.
Thank you very much, sir. Thank you,
Sir,
sir.
thank you. Finally, thank our Shanmugh sir and Dr. and Ponsan Kumar for yes, sir. Yes, sir. For our report. Thank you, sir. Thank you, sir.
Thank you very much, sir.
Thank you, sir.
Thank you, sir. Thank you, sir. Thank you, participants. We will assemble for our next section, that is afternoon section. Kindly join us 3 p.m. Okay. Thank you very much. The feedback link and all our faculty, Balakrishnan sir will send you. Kindly fill up the feedback form. And the feedback link we will send you through WhatsApp. Okay, no issue. Today only. The feedback link for section 1 and 2 will be sent you through WhatsApp. Okay. Thank you very much.